Okay. So I have tried to summarize the important parts that we have to consider. And for each one of these, not all of these apply. Okay. But like the ones that are further down. Okay. So we're going to focus on just dissociating ionic compounds, and we're going to do calculations based on solubility. So, but not everything's going to be a solubility calculation. So solubility is always going to depend on the concentration of each ion. The ions don't have to come from dissolving a compound. They can come from a reaction. So, but it's going to depend on the concentration of each ion. And so we're just going to be looking at first dissolving something in pure water. And so if it is pure water, it's just water. And so it will not contain any ions before you dissolve the substance. So if we just use distilled water, the distilled water should not have whatever ions already present in the liquid. If a solution forms, the definition of a solution or the synonym is homogeneous mixture. So if it is homogeneous and a solution forms, that means every bit of the solid is going to dissolve. So if it was heterogeneous, you would see solid, and if it becomes homogeneous, then that means that all of the solid has been dissolved in the water, in this case, the solvent, which is going to be water. So if we write the dissociation equation, it's going to be one way, because the arrow indicates what you see once it kind of everything happens or reaches equilibrium. So if it is one way and it points away from your substance dissolving, then it will point just toward the ions that form, meaning there's no more solid. However, if you reach what's called saturation, which is the most solid that can dissolve, if you go past that and you add more than the maximum amount, then you're going to reach supersaturated, which is going to be equilibrium. And so up to when it gets saturated, you can keep adding solid and it will keep dissolving. But at some point, because the solid particles have to be surrounded by the solvent, and there has to be enough energy that the water can break the ionic bond, at some point, there's not going to be enough available water and enough available energy to break any more ionic bonds. That's when you reach the saturation, which is solubility. And solubility is just the most that can dissolve. So you can look up any compound and find out its solubility in whatever solvent. So with organic, I do that a lot, because I try to find, for recrystallization, I try to find a solvent that's not really good for dissolving something, but not completely bad. So if something is highly soluble, the solid will dissolve easily. And so if it dissolves, it's going to be hard to get it back out. But if you want the crystals to come back out, it needs to be able to dissolve, but then also be not dissolved. So like dissolved at high temperatures when there's more energy, and then not really soluble at low temperatures. And so just as an analogy, if you make sweet tea, you have to dissolve sugar in it. It's easier to dissolve the sugar when it's hot, when the solution is hot. And so if you start off with like concentrated tea that's hot, then you can dissolve the sugar and then you can add water to dilute it. But if you try to dilute it first, even though you'll have more liquid, if it's colder, it's going to take more time to dissolve the sugar, and it might not all dissolve. So you might end up with a layer of sugar. That would be supersaturated tea. Does that make sense? Okay. Sugar, though, is not ionic, but all solids, this happens. Liquids, this is not true. This is not true for liquids, but for solids. And so if you reach supersaturated, then that's going to be equilibrium, because you have added more solid that can dissolve. And so the arrows would point both ways, which would indicate that there's solid and there's dissolved. So I'm going to make two different mixtures. And the first one is going to be the sodium carbonate. So the way that we determine whether it is supersaturated or not, if you ever see a molarity of an ionic compound, molarity means that is the amount dissolved solution. If it is not dissolved, there's no molarity. So molarity is the concentration in solution. And again, it's kind of like a circular argument here. If you have a solution, it means that it's homogeneous, which means it all dissolved, which means it's not solid, which means it'd be a one-way arrow. Okay. I made it real obvious for these examples when it was supersaturated, but if I didn't put that amount there, then it would be supersaturated. Okay, so if we're going to make sodium carbonate and it's going to be a certain molarity, that means that it should be something that completely dissolves. So the way that if you did an experiment, the way that you would know, or if you saw a container, the way that you would know that it was a one-way ionization is if when you looked at it, you did not see any solid. So if I add, this is sodium carbonate. If I add sodium carbonate to this beaker, it's a solid right now. So we're going to write down Na2CO3 solid, because the general format to show the dissociation of ionic compounds in water is you start with your ionic compound. As a solid. That's from last week. So you always put that, and that's the only thing on the reactant side. But we have to account for water. And so where do you put water? So you feel like you need to put water somewhere. Where did I say that you should put water when you write it down? On the arrow. And so there's two types of arrows. We either do one way, and you would do H2O, or you do equilibrium, and you write H2O. So we have to decide, do we do a one way in this situation or a double? This indicates right here that it is a solution, that we are below supersaturated. What you would see to kind of make this, what we write down, be a visual, if it is one way, that means that how much of the sodium carbonate should disappear? All of it. And so here is the solid right here. And so I'm going to put water. There's a hole somewhere in this spray bottle. So there, I've got water on top of it. And they're still solid because I haven't stirred it. I'm just going to give it a moment. Okay. It takes a while for solids to either dissolve or not dissolve. So whatever kind of arrow, that's just a little tiny detail that you figure out based on your information. But how you write the products is always going to be the same format. And so what do we put? How do we write this ionic compound as aqueous? What do we do to the ionic compound? You split it into the cation formula plus the anion formula. So the general format, you would have your cation plus your anion. And as coefficients in front, this is going to be our mole to mole ratio. So whatever the ratio is for our ions, that will be your coefficients. You do not put a subscript for an ion that is not part of the ion formula. So this is sodium carbonate. So we have to write the ion for sodium and the correct ion for carbonate. And so we write Na +1 and carbonate -2. And we make them both aqueous because they're the dissolved form. So sodium is not Na2, it's Na. What is the ratio of sodium to carbonate in our formula? 2:1. It's still, it's getting there. It's still dissolving. It's a hydrate, and so the first bit of water got pulled into some of the crystals, so the crystals became bigger, like they were really fine. And when water gets pulled in, they become bigger crystals. And so the fine crystals became tied together by water, and so now they're having to break up. But it's getting there. Okay, so that's, we're still gonna let that dissolve. Okay, so one way, because every bit of our solid is creating sodium and carbonate. So this is not an equilibrium situation. I'm going to go ahead and show you how we're going to use this in terms of keeping track of amounts. So I want you to take this dissociation and we are going to rewrite it right here. So you see how that's 0.75 sodium carbonate? I want you to rewrite the dissociation right here in the row that says reaction. And I have 3 columns because that will be the sodium carbonate, and that will be the sodium, and that will be the carbonate. Okay, so I created a rice chart for each one of our examples. So we're just going to continue on to the next page. And so just rewrite the dissociation here for practice number 2. So what we are going to do with every example is we have to have a chemical equation, also referred to as a reaction. It's a physical reaction, but still it's a reaction. So in order to keep track and create a rice chart and do any kind of calculations, you have to have the reaction. So the previous equilibrium stuff was actually reactions. And if you needed a chart, I asked you to rewrite it so you could create it yourself. But even if you didn't need a chart, I wanted you to look at it so that you could create the equilibrium expression. Everything that is in this section, we have to write our own reaction that then we will use to do the rest of the stuff. So that's step 1, which is either write out the reaction or look at the reaction given. It's still going to be the same, but for things that are dissolved in water, we have to create our own. So this is like the most important step, because everything that you do from here is going to be based on a ratio of 2:1 and the states of matter, and whether you decided if it was one way or an equilibrium. Okay. Okay. So our next is, what do we do if it's supersaturated? So if it is supersaturated, then we're going to have more solid than can dissolve. And so what that would look like, I've just got 3 little specks left. Okay, so you see how that's mostly clear right there? Just let me move the white paper out. Nice. You can't see. It looks all dissolved. And so that is visually what you should think when you see a one-way arrow when it's a solid dissolving. If it's one way, that means you do not see any solid. If it is supersaturated, the way that you ionize it will look the same. The only difference is the kind of arrow. And so I'm going to represent aluminum chloride. This here we have solid. Actually, aluminum hydroxide, but it is aluminum. It would take so much aluminum chloride to be supersaturated. I didn't want to waste all that because aluminum chloride is very soluble. I would have had to probably put 50 grams in here just to make it supersaturated. So, okay. So, you're still going to do the ionic compounds. And the first thing you want to write is the ionic compound. Don't start with me typing it. Always write it. Okay. And so you would start with aluminum chloride solid. And if it's supersaturated, there is no molarity there because it's not all dissolved. And so we are at a supersaturated point. So what kind of arrows do we use? The double equilibrium arrows. We still put water on top, so everything looks the same except for the kind of arrows. And the arrow is going to dictate what we do mathematically. Okay, so what would the cation be? Aluminum. And so you would write Al, but if you just write Al, that's metallic. To make it ionic, you have to put +3. So we got +3 because we got to make it the cation. And so the ion formulas have to be ions. Okay. What would you write for the chloride as its ion? 3 Cl -1. Again, the ion for chloride is not Cl3. It's a 1-to-3 ratio. The ratio, the molar ratio, are the coefficients. The chloride ion is always Cl -1. The subscript in a chemical formula is based on the charge of the cation it's bonded to. Okay, so this is going to be equilibrium. So when I add water, what should I still see after a few minutes? I should still see solid, and you won't see the ions. The thing is, you won't, like, we cannot, now this other solution, we don't know there's sodium carbonate in there, other than the fact that you saw me dissolve it. And so if you just saw that, it would look like water or some clear liquid. You have no idea, unless it's labeled or you saw it happen or you did it yourself. So with this one, I just put water in here. If it all dissolves, I'm just going to add more solid. So if you want it supersaturated, if you want a supersaturated solution, it's the way that I do it. I just put some solid and water together and I stir it. And if it all dissolves, I add more solid. If it doesn't all dissolve, I'm done. Probably a better idea if you don't know kind of how much that you measure out more than you need. But I've been doing this a long time. So, okay, so here it is all cloudy. Cloudy means you're solid. So I'm just going to still let it sit there. And so it's going to take a little while because we want the ions to dissolve. So it's going to take a while for that to happen. And so we need to know that we've had enough time for any ions to dissolve and there still be solid left over. But because it is equilibrium, this is going to trigger all of the equilibrium stuff, which if it's equilibrium, step 1 is write out the expression. Write out the reaction and then use the reaction to write the expression. So if it's equilibrium, it's going to trigger the 4 equilibrium steps, which is after you write out the reaction, you write the expression. And so what would the expression be for this equilibrium? So see if you can write out what the equilibrium expression would be, which is the math equation. any equilibrium situation, whether it's a reaction or a dissociation in water of a weak acid, a weak base, or supersaturated ionic compound, there is going to be an equilibrium expression associated with it. And so we're going to have the equilibrium constant, and it's always going to be equal to your products over reactants when they're in the same phase. And these are not going to be gas situations because these are all in water. And so it's going to be all the aqueous things. So anything aqueous in any of our dissociations that are equilibrium will be part of the expression. So our ions are going to be part of the expression. And so our aluminum concentration times our chloride, and our chloride is going to be raised to the third, and our aluminum is going to be raised to the first. What about the reactant side? It is a solid, and so for anything that's not in the same phase, you just replace it with, you have a 1 as a placeholder for it. The 1 is important so that you don't get confused. And the two confusing parts would be, you think you need to include it. It doesn't have a molarity because it's not in the same phase. Only thing with a molarity are the things dissolved, which are the things that are aqueous. Okay, so if it dissolves, it becomes these ions. Solid substances do not have a molarity. Or worse, you think that you need to put a 0, and then that would make the whole thing undefined. So just put a 1 there, and that shows that you are accounting for its presence, but it's not going to factor into the expression because the expression is based on how much of this is floating around in the water. How much dissolved. Okay. The K is a specific kind of concentration constant. So it's a specific kind of K sub C. K sub C is concentration, molarity. Okay. This is based on the solubility. So every single one of these is going to be a solubility related constant. And so the solubility constants are referred to as the solubility product constant. Product being on the product side and plus the multiplying them together, that's also a product. So it is the product being multiplication of the solubility of the compound. And so the constant is called the KSP. And guess what SP stands for? Solubility product. Again, it's only the constant when you are referring to the solubility of a substance and you have multiplied the concentrations of each of the aqueous forms together, the product, what it forms. Okay. And so this is the KSP. This is not the solubility. Solubility is the actual concentration. This is when you take the concentrations of each of the ions and you multiply them together, then you get the constant. So here's our solution. Okay, so just tilt it to the side. So you can see that the liquid looks clear. So there is a homogeneous mixture on top, but look at the bottom. Can you still see there's white solid? And so above that white solid, because I've let it settle, above that white solid is the aqueous ions. But in this mixture are the aqueous things and the solid. And so right now, at this point, what's happening, to visualize it, the solid is still creating the ions, but at the same rate that the ions that are floating around are coming back together and turning back into the solid. And so there's just a constant where the water is going in and breaking up the ions. But as ions enter the solution, now there's going to be too many. And so the ions in solution come back together and go back to being a solid. That's the equilibrium. Okay. So go ahead and either copy the ionization from last week or redo the ionization here. And if it's supersaturated, that's going to trigger a KSP expression. If it is not supersaturated, you do not do KSP because it's not equilibrium. And so I'm going to put a note here. It's going to be not equilibrium. So any of the ones that are not equilibrium, I want you to make a note to yourself that it's not equilibrium. If it is equilibrium, then we're going to do equilibrium. And anything that's equilibrium, that's going to trigger step 2, which is the expression.